Hello, everybody. Here we are, 6.1 graphs of relations. And just to start, a little bit of what I think will be review, that the x-axis is the axis on a graph that goes left to right. So this one right here is our x-axis. And that the y-axis is the axis on a graph that goes up and down, this one right here. And that a relation is a relationship between two sets of values that can be graphed. So ordered pairs, our ordered pairs are always in x, y. So it's two data points and the relationship between those two. So this first part is about interpreting graphs, and a lot of it is kind of, trying to figure out what story the graph tells or matching a story to a graph. So match each graph below the likely situation from the list provided. Label each axis with its own title. So we're going to be labeling the y or the x, and we got to match each of these scenarios with the graph we think kind of matches it best. So let's do the first one, the temperature of a cup of hot chocolate over time. So, I don't know if you're much of a hot chocolate drinker. It starts quite warm. It can stay warm for a bit and then kind of like becomes quite cold quite quickly. So I would say the one that seems to match this is graph C. And I would say this is time. And on the other side, we have the temperature. So it starts quite hot, kind of cools, and then kind of reaches a kind of plateau of coldness, and you don't want to drink it anymore. Maybe warm it up in the microwave. The next one, a car accelerates to a constant speed. So it accelerates, it kind of moves quickly in one, its speed increases quite quickly over time, and then it reaches a constant rate, and then it kind of flattens out. Okay, so I would say this looks like this is graph B, that we, accelerate here. We're kind of quickly, that not much time is moving, and our speed, which I would put at the side here, over time is increasing in a short amount of time. And then we even out, maybe, you're accelerating to 60 kilometers per hour or something like that. The next one, the distance a person walks during a hike. Okay, let's see which one of these makes sense. I mean, A doesn't seem to make sense. You'd be walking. It seems to make sense until about here, but then your distance wouldn't decrease as you continue to go. This one might make sense if it was like, the distance from your starting point as you go on a hike. But I think graph D seems to make more sense, that, the distance increases over time. I would put time on the bottom again, and then distance on the side. And this one, I don't know how accurate this one would be. I don't think we're kind of perfect walking or hiking machines. We're not kind of walking at a perfect distance. Maybe you'd be walking a little bit slower or whatever. But I think good enough for our purposes. And the last one, I like this one. You can almost kind of see it, the height of a soccer ball kicked across the field. I mean, process of elimination, but I feel like you can almost see the soccer ball, can't you? I would say height at the side. And then you can maybe do distance or time again at the bottom, so that your kick kind of looks something like this. Probably it would actually be a bit flatter, but then you have a nice peak and then comes down on the other side. Okay, so we kind of made sense of these four situations and matched them to a graph. So you'd be doing some of that. Next, we have a little bit of information just about how slope affects a graph. So the steeper the slope, the faster the change is occurring. So, you can imagine if this were like the car accelerating one, that this car, if we, accelerated to a flat rate, is accelerating quicker than if you say, let's maybe extend this one, accelerated to the same speed. This one is accelerating much quicker than this one is. It's going faster over a shorter period of time. And the other one that right here, that the shallower slope, the shallower the slope, the slower the change is occurring. This one, maybe you could imagine again our hot chocolate. So maybe you have it in a thermos, and so it stays hotter longer. Maybe it takes much longer to cool. And then this one might just be in a regular mug. It cools quite quickly or something like that until it's cold. So the shallower the slope, this is a less kind of shallow, this is a steeper slope, the slower the change is occurring. And if we have no slope, the slope equals 0, a horizontal slope, no change is occurring. So this is kind of like, well, maybe in the next example, or when we reached a constant speed, or you'll see this a little bit kind of on our next example. So let's look. Example 1, interpret a graph. I don't know how popular wakeboarding is, and I don't know that much about it. So I'll do my best to interpret it based on what I think I know. So wakeboarding has grown to be a popular water sport. Okay, I'll take your word for it. The graph shows the distance that a wakeboarder is from her starting point on Last Mountain Lake in Saskatchewan. Describe what the boarder is doing. So what's recommended is, in order to solve this problem, we need to look at each change in slope as an event. So we're going to look at this part as an event. We're going to look at this part as an event, this part, this part, this part, and this part, all as separate events. And let me erase that mess, and maybe I'll type out my best interpretation with my limited understanding of wakeboarding. So from A to B, it looks like we're kind of going a steady distance from the start. So maybe say traveling a steady distance from the start. From B to C, so we're either kind of not moving any further. So this might be the part where you're kind of like waiting to start your run. I don't know what it's called when you're wakeboarding. Steady, constant distance, I guess. And so you notice that the time is still going on, but the distance isn't moving. So this suggests that she's still in this moment. So she's not getting any further from where she started, but time continues to move on. And then from C to D, the quick acceleration. Away from, I'm going to call it the dock. I guess that's where I'm thinking that we're starting. And then again, from D to E, another kind of quick acceleration towards. So we're getting closer now, the dock. So maybe, I don't really know, but it seems like, you're waiting. The boat now has started. You're picking up speed, and I don't know if they tend to turn around. Maybe they do. I don't know a lot about wakeboarding. You can let me know. We're kind of having another quick acceleration. And then from E to F, waiting again, / no change in distance. So maybe if there's like several boats, maybe this person is just kind of waiting to return to the dock. So time continues to move on, but the distance doesn't change. And then from F, G, kind of steady pace back to the starting point. Okay, that's my best interpretation of this with my limited understanding of wakeboarding, but I think those are reasonable assertions. We're kind of doing a slower acceleration away from the dock here, waiting to do the kind of like exciting part. Then the boat's going fast this way, boat's going fast kind of back towards the dock. Now we're waiting again, and then a kind of slower pace back to where we started. When I clicked away from this a little bit ago, it kind of deleted it all. So maybe I'll just leave that there for a second. Maybe I can pause it, or I'm going to click away and hope for the best. Oh, it worked. Okay. The last one, the bell just went. I'm going to try to squeeze it in here. But so last one, which graph best represents a person's height as a person ages, and explain your choice. So this one, they kind of have a similar start to it, but I think it's this part, the kind of second part of the graph, that I think kind of distinguishes the graphs in which I think we should focus our time. So here we have, constantly our height is growing. Then we make a very short peak, and then we kind of a quick decline, quite a significant decline. This one seems to be pretty reasonable. We have an increase, could be there, a little steeper increase that could be at puberty. Then we have a kind of constant part where they're the same height for quite a long period of time, and then a gentle decrease. Here we have a same kind of growth, but then this point that I think doesn't really represent height. We do kind of tend to have a constant phase and then a shorter decrease, which I think is better than this one, but still not as good, I think, as graph B. And the last one kind of have, a nice gradual thing as you grow, not much of a steady part and a slight decrease. I think that our best graph is B. Thank you so much. I'll let you know what textbook questions I'd like you to do.